Hello, so for this video, we will present our project with the title Facial Expression Recognition with PyTorch and Transfer Learning. So we are from Group 8, and this is our team member, Jeremy Jalong, Jeremy Jos, Sarvin, and me myself, Otnif Cliff. For, uh, for today's presentation, this is the agenda, introduction and problem statement, dataset FER 2013, methodology and implementation, meaningful modification, experiment and result, analysis and discussion, and also lesson learned. Okay, why facial expression recognition? So for the applications used to mental health assessment, human-computer interaction, driver monitoring system, educational technology, market research, and the challenge is subtle difference between emotion, cultural and individual variation, lighting and pose variation, and also real-time processing needs. So our goal is to build an accurate FER system using deep learning. So for the data set FER 2013, there are 7 emotion classes. The first classes is angry, which 4,953 image. Disgust 547, fear 5121, happy 8989, neutral 6198, sad 6077, surprise 4002. So the total is 35,887 facial image, which grayscale 48 times 48, and class imbalance discussed severely underrepresented 1.5%. Next, I will pass to the next presenter.
Right, thank you. Moving on to the methodology overview. Our foundation, we use ResNet 18, pre-trained on ImageNet, applying a transfer learning approach. We developed the project in PyTorch using Google Colab, Tesla T4 GPU. We compared a 100 epoch baseline against a streamlined 20 epoch modified strategy using the Adam optimizer. Now, meaningful modification. To fight overfitting, we made 3 changes. Number 1, custom classifier head, added 512 to 512 to 7 architecture with dropout 0.5 and batch norm. Number 2, fine tuning. Frozen layers 1 to 3 to keep core features, making only layer 4 and the classifier trainable. And then lastly, for regularization, integrated weight decay and a learning rate scheduler to sharpen optimization. Why? To combat overfitting and improve generalization. Next slide. And then model architecture diagram. This diagram illustrates the pipeline. Input image are processed through frozen blocks, then fine-tuned in layer 4. The 512 feature vector passes through our custom ReLU ataupun dropout head, ending in a softmax layer to classify the 7 target emotions. Then next, experiment design. We ran 2 experiments. Experiment 1, baseline versus modified. Objective is to evaluate regularization impact. Control same dataset, same epoch, variable architecture modification, and then for metrics accuracy, F1 score, and loss curve. And then for experiment 2, data augmentation, the objectives and the objective is to assess generalization improvement. And then for variables with or without augmentation, and for augmentations, random flip and rotations. And then for the metrics is validation accuracy gap. Thanks. Okay, this is for our performance metrics. Our results highlight a classic trade-off. The baseline overfit significantly, hitting nearly 100% training accuracy, but failing to generalize. While the modified model was 5 times faster to train, The modified augmentation version was our top performer, achieving the highest test accuracy, which is 68.12%, and F1 score 0.67. This confirmed that regularization and augmentation are essentials for real-world performance. So for me, thank you, and I will pass the next slide to the next presenter.
Next, I'll explain the training dynamics of both models. For the baseline model trained for 100 epochs, the model converged very quickly. It reached over 95% training accuracy within the first 10 epochs. But after 20 epochs, the validation accuracy stopped improving. This means the model was memorizing the training data rather than learning general facial features. For the modified model, training was slower because of dropout and batch normalization. The loss curves were more stable, which indicate better regularization, but the validation accuracy was limited. In conclusion, although the modified model trained more smoothly, overfitting remained the dominant challenge. Next. This slide compares the validation accuracy between the baseline models and during the first 20 epochs. The baseline model peaked at about 65.8%, while the modified model peaked at 61.2%, which is about a 4.6 drop. The main reasons the modified model underperformed are likely over regularization, especially using a dropout rate of 0.5, and the reduced effective capacity of the model. Additionally, the model was trained for fewer epochs, which may not have been enough for it to fully converge. This highlights that while regularization is important, it must carefully be balanced. Next. Now I'll move on to error analysis. From the confusion matrix, we found that the most common misclassifications were between fear and sad, disgust and angry, and neutral and sad. These errors make sense because these emotions pair very similar facial features, such as brow position and mouth shape. The best performing emotion was happy, with a recall of over 90%, likely because happy expressions are more visually distinct. On the other hand, disgust performed the worst, mainly due to severe class imbalance as it had very few training samples. This analysis shows that some emotions are inherently harder to distinguish, especially with limited data. Next. Lastly, I'll talk about the impact of data augmentation. Without augmentation, the model trained faster but showed a larger overfitting gap, with validation accuracy around 61%. After applying augmentation techniques such as random horizontal flipping and small rotations, training becomes lower, but validation accuracy improved to around 67%, which is an improvement of about 6%. This clearly shows that data augmentation significantly improves generalization, especially for smaller datasets like FER 2013. In summary, data augmentation turned out to be one of the most effective techniques in improving our model's performance. I'll pass it to the next presenter.
Thanks, Josh. Key findings. First, transfer learning works. Pretrained RESNet 18, effective for FER, achieve 65% accuracy baseline. Second, overfitting is major challenge. Trend gap 35% needs stronger regularization. Third, data augmentation crucial, improves generalization by 6%, essential for small datasets. Fourth, regularization trade-offs, dropout stabilizes but may reduce capacity, need careful hyperparameter tuning. Challenges faced. First is technical, Google Colab timeouts, 12-hour limit, GPU memory management, long training times, 5-minute epoch. Second is conceptual, balancing regularization versus capacity, interpreting confusion patterns, class imbalance handling. Third is collaboration, coordinating across 4 members, version control without GitHub, time zone differences. Lesson learned. First is technical skills, PyTorch implementation workflow, Google Colab plus Drive integration, model evaluation and visualization, deep learning concepts, transfer learning practical application, regularization techniques, overfitting identification and mitigation. Third is project management, team coordination and communication, documentation importance, time management for deadlines. Future improvements. First is architecture exploration. Vision transforms with efficient net, mobile net V3, attention mechanisms. Second is advanced techniques, class balancing, oversampling, gradient accumulation, ensemble methods. Third is hyperparameter optimization, systematic dropout, search, early stopping implementation, learning rate warm-up. Fourth is real-world deployment, real-time video processing, mobile app integration, privacy-preserving techniques. Thank you. That's all from us.